Now, in this video, we're going to attempt to demonstrate the simplifications in calculating the Fourier coefficients when the function is even. Now, we know from our discussion before that with an even function, the b sub k's will be 0 for all values of k. Let's just look at the situation here. First of all, looking at the odd harmonics, so looking at the k equals 1, 3, 5. When k equals 1, you have a cycle, one complete, in this case, sine wave cycle, in the same period as the even function. When you multiply it, you've got, during this quarter wave here, you've got positive times positive. That gives you a positive area. But during the second part of this first half of the period, you've got positive times negative, which gives you a negative area. And again, when we integrate, the positive areas are equal to in size to the negative areas, and integrating them, they cancel. So the b sub k's that arise from taking this even function and multiplying it by the odd function sine, and then integrating that product, the b sub k's all go to 0. On the other hand, the a sub k's, which are the coefficients that we find by multiplying our even function by the cosine term, we have then, here's our even function, and as you can see, the sine or the cosine wave aligns with it. You have a positive times a positive and a negative times a negative. Once again, you're going to get a positive bump, and the negative times negative is a positive bump, so that when you integrate this product, you get a non-zero value. Hopefully you're seeing that it all has to do with the way the cosine function lines up in phase with the even function, but the sine function lines up 90 degrees out of phase with the even function. And it's that out of phase that causes this negative positive here, but we don't get the negative positive here because you got the positive positive and negative times negative. So for an even function, the a sub k's are not 0, the b sub k's will be 0. Here we introduce the fact, we look at the fact that f of t is also half-wave symmetrical. We've already demonstrated that the b sub k's are going to be 0 for all values of k due to the even nature of the waveform. Let's look now at the a sub k's and see if we can understand why the a sub k's equals 0 when k is an even number. When k is even, for example 2, we get two complete waveforms of our cosine term in a single period of our even half-wave function. There's the period of the even function, half-wave function, and there's 1, 2 complete cycles when k equals 2. So we end up with a situation where during this part of the positive lobe of our half-wave function, we've got positive times positive gives us a positive area. Now during this part of that, you've got positive times negative giving you a negative area. So within a half a waveform, you get one complete oscillation of the cosine term that's oscillating at twice the frequency of the f of t. And with that complete oscillation, you get as much positive times positive as negative times negative, which when you integrate that product, again, that area and that area and that area and that area all add to 0. So, when the function is even and half-wave symmetrical, the b sub k's are all 0 just due to the even, and the a sub k's will be 0 for k being even values.